Hello everyone, my name is Namho, and today I will walk you through my implementation of the light field processing and focus stacks and depth from defocused for assignment 4. The goal of this project is to take a single light field image captured with a PlanOptic camera and extract multiple capabilities from it, thus generating different viewpoints, synthetically refocusing at different depths, and computing an all-in focus image along with a depth map. We'll be working with the following image here. So this is a chessboard stage from the Stanford Light Field Archive. The input image is 6,400 by 11,200 pixels, captured with a PlanOptic camera that has 16 by 16 lenslets, each covering a 16 by 16 pixel block. This gives us a 256 different viewpoints of the same scene. Now, let me dive into the four main parts of the implementation. The first challenge is organizing this massive image into a useful data structure. So if we look at the initials .py script on the left-hand side, you'll see that in figure 1 here, the key function here is load light field, as you can see here. Starting at line 5, the goal is to create a 5-dimensional array L indexed by UV-STC, where UV represent aperture coordinates, giving us our 16 by 16 sub-aperture positions, and ST represent the spatial coordinates in our lenslet array with resolution 700 by 400, and C represents the 3 RGB color channels. Now, looking at lines 22 to 24, we first calculate the grid dimensions. So 6,400 divided by 16 gives us 400 lenslets vertically, and then 11,200 divided by 16 gives us 700 horizontally. That's in total 280,000 lenslets. The reorganization happens in the nested loop from line 29 to 40. For each lenslet position, we extract the 16 by 16 pixel block from the input image, and then distribute each pixels to its corresponding position in the 5D array. Each pixel at position UV within lenslet block represents a ray through the point on the aperture. Now, the result is about 205 megabyte, is a 205 megabyte array, and it's with a shape of 16 by 16, 700 by 400, and 3. And at line 56, as you can see here, we verify correctness by extracting the center sub-aperture view, which you can see here. It looks like a pinhole camera image on the chessboard. Now, since we have the 5D, our 5D light field, let's now extract the 256 sub-aperture views. At line 50, this is in sub-aperture views.py in the script. And if we look at figure 2, as you can see here, figure 2, the function at line 6 is pretty straightforward. Here, extract sub-aperture views. Line 22 shows you how each view is simply a slice of a 5D array at a fixed UV position. And so so if you look at line 22, this resulting array is the entire spatial image of the aperture position. So I guess the most interesting part is creating the mosaic. So the mosaic, so I have a function called create mosaic, and in this function, starting at line 26, we arrange all the views, all the 256 views into a single large image. And the lines 49 to 56 shows the arrangement logic. So if you look here, we in this nested for loop, the vertical axis corresponds to the increasing U values, and the horizontal axis corresponds to the increasing V values. So if you look at the resulting mosaic, which is you see here, it's 6,400 by 11,200 pixels. And if you really look closely at the adjacent views, here, you'll notice objects shift positions ever so slightly, and this is the parallax effect, as we discussed in class. thus confirming that our light field organization is correct, and objects closer to the camera shifts more between views than distant objects, which is exactly what we expect from the different viewpoints. Now, for the most computationally interesting part is the synthetic refocusing. So if we look at the refocusing.py script, if you look at figure 3, the algorithm implements two equations. So equation 1 at line 18 in the code base is simply averaging across all sub-apertures using NP-mean over U and V dimensions. So this produces an image focused at default depth. The real magic is actually in equation 2, implemented in the refocus equation 2 part, as you can see here in line 21. This is where we focus at different depths, and the key is the lines 44 to 54. So for each sub-aperture, we shift the image by an amount proportional to both the aperture position, UV, and the depth parameter, D. And moving forward, in line 74, we show how we use the utility function, create the centered coordinates. And here, to our center, essentially this enables us to center the aperture coordinates. And this is very critical because instead of U and V ranging from 0 to 15, they range from negative 7.5 to positive 7.5. And this centering is essential for correct refocusing behavior because shifts must be computed relative to the central ray. We use SciPy ND image shift at line 48 to 54, right here. And with bilinear interpolation, order of 1, for sub-pixel accuracy. So for each sub-aperture, it gets shifted by D times, and each aperture position, then all shifted images are averaged together. So looking at the main function at line 111, as you can see here, we generate 15 depth slices spanning from negative 1.0 to positive 1.5. So negative D values focus on farther objects and positive D values focus on nearer objects like the top of the chessboard. Now, if you look at figure 4 down here, so these were the resulting for figure 3, and for figure 4, you can see the effect clearly in the results. At D equals negative 1.0, the background is sharp, and at D equals 0.25, the middle depth is in focus, and at D equals 1.5, you can see here, the top of the chessboard and the nearest chess pieces are sharpest. So the focal stack stores all 15 of these in the 40 array. So in the next part, I guess the final and most complex part uses the depth from defocus to create an all-in focus image and depth image. And this is implemented in depth from focus.py, as you can see here. The algorithm has 6 steps. First of all, at line 8, and the corresponding implementation is outlined in the report, but just to go through the code base, in line 8, we have convert to luminance function, which converts each focal stack image to an XYZ color space and extracts the Y luminance channel. And if you look at line 24 to line 26, it shows this actual exact conversion. And next, you have compute sharpness weights, which starting at line 30, actually implements the core depth from the defocus algorithm. So for each depth slice, we apply the Gaussian blur, which is in line 53. We apply the Gaussian blur with sigma 1 to create a low frequency component. And then we subtract this from the original to get the high frequency details. And then we square the high frequency components. And lastly, we apply another Gaussian blur at sigma 2, as you can see here. And this produces weights indicating how sharp each pixel is at each depth. And the intuition is that pixels are sharpest when they're in focus. So higher the weights indicate the correct depth. And the compute all image function here at line 65 uses these weights. And looking at like 79 to 86, we compute a weighted sum of all the depth slices for each color channel, and they're normalized by the total weight. This essentially allows us to select the sharpest pixel value from across all depths. Now, similarly, the compute depth map function as you can see in line 92, computes a weighted average on the depth values themselves. So line 108 to 109 shows this calculation. Instead of averaging pixel intensities, we're averaging the depth parameter D. Now, the tricky part is parameter tuning. So we tested 16 combinations of sigma 1 and 2, shown an experiment with parameters, as you can see at the bottom here. And the function at line 114. So from 154 to 155, we define our test of values, as you can see here, and which are sigma 1 being 1, 2, 3, 5, and sigma 2 being 1, 3, 5, 10. Here's the basic parameter tuning comparison table. So sigma 1, it controls detail preservation. So what this means is lower values keep more details but introduce noise, whereas sigma 2 controls depth map smoothness, which lower values give detailed but noisy depth maps, and higher values produce smoother results but may blur boundaries. Now, after testing the 16 combinations, we found that the optimal parameters are sigma 1 when it equals to 2 and when it is equal to 5. This gives us an excellent balance between the sharpness and the smoothness. And if we look at figures 6, 7, the final all-focus image shows every part of the scene. It has a sharp focus from foreground to background, and the depth map clearly shows the scene geometry, with brighter values representing the nearer objects and darker values representing the farther objects. Now, I just wanted to highlight some important findings and like the decision-making process. So the 5D array structure proved highly effective for capturing the complete light field, as it enabled both like viewpoint changing as well as refocusing from the single capture, which is something that we learned that was impossible with traditional cameras in class. For refocusing, by centering the aperture corners was very essential. And you can see this in the utils.py script here, where from line 16 to 19, the coordinate centering ensures shifts are computed relative to the central array, which is physically correct. We choose a bilinear interpolation for good balance between quality and speed. So higher order interpolation would be more accurate, but significantly slower given that we're processing 256 sub-apertures at each of 15 depth. Memory management was a bit of a challenge with the 205 megabyte light field array, so we saved the intermediate results to disk between the processing stages to avoid memory collapse or issues. And the depth from defocus algorithm showed significant parameter sensitivity. So the systematic experimentation that I showed across the 16 parameters was necessary to find the optimal value. So, different scenes might require like different pairs and combinations, different parameters specifically. But the choice of sigma 1 is equal to 2 and sigma 2 is equal to 5, which worked well for our chessboard scene. So in conclusion, this is the video presentation for the light field processing pipeline, and starting from the 16,400 by 11,200 pixel image, we completed the entire pipeline, and the results are shown in this report. Please feel free to run the code base following the Conda environment installation. And thank you so much for listening.